Welcome back, students. So, today I will be trying to give you something different, which probably we have talked it, but not in detail. We will be trying to discuss synthetic equivalents. Synthetic equivalents. So, synthetic equivalents, as I discussed earlier, sometimes also referred as synthons. Now, synthon, the term first invented by Professor E. J. Corey, who is also the principal fellow who first coined this term retrosynthesis. Now, Professor Corey's definition for the synthon says that if you having a particular two different unit as your target molecule, you can simply do a disconnection based on A minus and B plus just by simply polarity addition, and you can make a new bond. Now, this A minus can be called as a synthon 1 and B plus can be called as a synthon 2. Now, this synthon concept probably is very well known, established earlier, but the terminology synthon nowadays are no longer used, is kind of a backdated. Now, synthon probably you can simply say that your carbon ion is a synthon, okay. Your acyl cation in the Friedel-Crafts reaction is a synthon. So, these reactions we already known earlier, but from this viewpoint we probably have not discussed. Now, you will find that if you having a negative charge on your synthon, these synthons are normally termed as a donor synthon or D, and if you have a positive charge, means that which can act as a acceptor or which can accept electrons, it will be termed as a acceptor. So, donor is basically stands for D and acceptor stands for A. Now, depending on the number of carbon this donor part is having, it is abbreviated as Dn and this is also An. So, n could be a integer, So, Dn and An is usually the terminological definition. Probably the very classic example from synthetic equivalent disconnection or synthon concept in terms of retrosynthetic analysis will be visible from this particular example, where you say that if you having this particular anion and this particular acceptor. Now, I am saying this one is a synthon 1. So, we basically do a disconnection there and this is your synthon 2. Now, this one is very stable, this is basically a enolate anion and this is your Michael acceptor. So, this is normally this is termed as a D synthon. So, you can call it D2, this is the 2 carbon or you can D2 and this is basically your acceptor system, just write acceptor. Now, number of carbon if you can count is 1, 2, 3, probably this 3 is basically involved, remaining part you can just exclude. So, it could be A3. So, this way you can basically do the retro based on donor synthon as well as acceptor synthon. And we have earlier explained that if you having a electron withdrawing group, this kind of synthons are normal synthons, because this negative charge can easily be stabilized. So, this is called normal synthon, where the polarity remains same. So, now, if you having a synthon something like this, where the negative charge resides on carbon. Now, normally carbon do not prefer this kind of charge, it always prefers this charge, because oxygen is more electronegative. So, this kind of synthons probably all of you know is referred as Ampolong synthon or reverse polarity, where the polarity has been reversed. and this is your acyl cation, which probably you have earlier came across in the Friedel-Crafts reaction. So, in this way you can basically categorize several synthons, normal and Ampolong synthon. As I said, the synthons are usually not commercially available, you need to prepare them in the lab. So, I am saying acyl cation is a normal synthon, but if you having a acyl anion which is Ampolong. Now, acyl cation is referred as A1 and Ampolong acyl anion is referred as a D1. Okay. Now, next your enolate. Enolate is absolutely known, is normal because the charge can be stabilized, but if you have a synthon like this which we call enolate cation. Now, enolate cation is absolutely not stable species. So, you say Ampolong. There are very few examples, we are not going to talk about this enolate cation. Now, you just change on the simple polarity, you will you can basically create different kind of synthetic equivalents. So, this is your A3 and this is a homoenolate cation. So, normally carbon prefers plus minus plus. So, basically charge reverses in this way, plus then minus enolate, then plus then minus. So, in this case it will be a D3, it is called homoenolate. So, this is just basically terminological disconnection. We are not going to talk in detail how these species are generated because it is beyond of our scope. Now, what I am trying to do, I will try to do some retro based on some target molecule, then I will find how several synthetic equivalents are basically helpful and how this synthetic equivalent of synthons can be easily generated. I am giving you a target molecule cis jasmone. This is jasmone. I will be doing a very standard retro because we do not have much time. So, if you do a standard retro through aldol transformation, you will find that you basically needing a this compound, this. Okay. So, you just basically need a aldol retro to make this molecule. Cis jasmone was used in the perfume industry. Next, what I am saying that if you can have a synthon something like this synthon, so what I am saying that now if you visualize that this particular central carbon act as a D1 Ampolong, so it is basically 2 D1 Ampolong, and then you react with a alkyl halide at this end, you get this one, and here you do a Michael type of reaction with methyl vinyl ketone. So, this is your acceptor synthon, this is your donor, this is also acceptor synthon. So, one synthon having two donor site, so it can react with the one acceptor in the left hand, one acceptor with the right hand. Now, this kind of 2D1 synthon is already known as a formaldehyde 1,3-dithione. Now, here we will try to disclose some other synthon. If you have formaldehyde, you react with sodium cyanide and react with Et2NH. You basically get a compound named as aminonitrile NET. How you get? You basically react first formaldehyde with diethylamine. You basically get this imine. Then your cyanide attacks in the iminium carbon through a nucleophilic fashion, you get this compound. Now, this aminonitrile is also acting as a D1 synthon. How? The hydrogens attached to it are extremely acidic because you have a cyano, you have electron withdrawing nitrogen containing group. So, now we will now try to visualize how this amino nitrile. So, N ET CH2 CN. First I am reacting with LDA. I am saying that this compound is acting as your 2D1 synthon. So, LDA and the first acceptor synthon, I am putting a bromo here, sorry, 1 carbon extra bromo. Then you see that NET2 remains similar, CN similar, one hydrogen is abstracted and you basically get this compound, fine. Next, another round of base abstracted this hydrogen and then you react with another acceptor which is the methyl vinyl ketone. So, you will basically get next you need to generate the carbonyl compound by simply doing a hydrolysis with copper sulphate in a acidic medium. Now, this hydrolysis was pretty obvious. Initially actually this copper sulphate and acidic pH first attack this amine to give you the OH here, and then basically this is basically converted to cyanohydrin, which then undergoing H chain elimination to give you the parent carbonyl compound. You will get this compound. So, which is our desired compound? You do the aldol and you can end up with the target molecule cis jasmone. So, what we now formulate in this entire synthesis? If you having a diethyl amino nitrile which can be visualized as a 2D1 species. This is a very unique reaction to convert the synthesis. Now, same compound this particular jasmone, the cis jasmone. Now, I am saying that this compound you can also make through a, or you can easily synthesize through another class of starting material, and here what I am saying that you can make this compound through this starting material as well as this starting material. Now, if you now try to analyze this retro in earlier sense, we will have the starting material. Now, this starting material, if you react with butyl lithium, the furan basically this acidic hydrogen was first removed and give a lithiated species. Now, this lithiated species and this one basically react to give you a CH2, CH2, CH2 double bond, these things. Now, furan compounds can easily be opened up to a 1,4 dicarbonyl compound just by aqueous hydrolysis, and then you will find that you basically get this 1,4 dicarbonyl compound. Now, this dicarbonyl compound, now we are basically visualizing the entire concept in terms of synthetic equivalence in this way, So, we are saying that a properly substituted furan, which is basically this methyl, can act as a RC double bond O CH2 CH2 C double bond O minus. Now, this is also ampolong, but it is a ampolong, the number of carbon has been basically increased. Now, what we say? We said that with this furan we are reacting with this electrophile whose electrophile structure we have already given. The furan initially was reacted with a butyl lithium and you get this minus and this methyl. Now, this minus is actually visualized as this MECO, MECO, CH2, CH2, CO minus, CO minus. So, once you do this reaction and after hydrolysis you basically get the product which is required for your Jasmine synthesis. Now, see the furan part is basically giving you MECO, CH2, CH2, CO minus, this minus, and then you are approaching the electrophile. Now, this one by similar way, if you do a aldol reaction, it will give you cis jasmine. Cis jasmine structure was already discussed you in the earlier slide. In similar way, you can basically carry out many synthetic experiences or synthetic exercises. Let us try to figure it out very simple synthetic equivalents. So, how you can make this compound? Now, if you see this compound can be easily made if you having a this particular dialdehyde and this as a electrophile. So, what you need to do? You basically cut here and visualize as a CO minus, CO minus. Now, this CO minus basically will be now reacting with this. So, this is basically donor synthon. This donor synthon will be now reacting with a this acceptor and this acceptor, which you have explained according to the Koresh terminology. So, donor synthon, donor acceptor. So, in similar way you can basically do the couple of exercises, a similar kind of exercises now I am be doing. I am saying you are given a target molecule whose structure is this. The starting material is which was given to you is this. Okay. So, what you basically need? You just need a MECO minus as a donor species. Now, this donor is a basically ampolong. I remember earlier we have also discussed this kind of ampolong you can also synthesize through O protected cyanohydrin, the chemistry which was first discovered by Professor Gilbert Stock, O protected cyanohydrin. Go back to your earlier lecture, O protected cyanohydrins. Professor Gilbert Stock was the instrumental for this reaction, where I said that if you having a O protected cyanohydrin, you can easily abstract this hydrogen and that can basically give you a very nice ampolong species. So, in principle 1,3-dithiene definitely you can use 1,3-dithiene chemistry. You can also use this O protected cyanohydrin chemistry as described. So, this is simple things. So, now how you can basically generate it? If you can take this compound as your starting material, the reaction is simple. In addition also you can take this compound or TMS cyanide. So, basically O protected cyanohydrin. So, both the chemistry you can easily do, and try to remember in our biological system also this kind of Ampolon chemistry was often very much in action. In our biological system, this kind of intermediate was very much in action, and particularly we have also discussed a stator reaction earlier. Stator reaction earlier, we say that stator reaction is a synthetically very useful reaction which is basically catalyzed by n heterocyclic carbene chemistry or n heterocyclic carbenes. And if you now try to do a simple disconnection of molecule like this 1,4 dicarbonyl compound, you can easily do the disconnection, followed by this. You can say that this is your donor, this is your acceptor. So, basically a Michael version of reaction, but where you use a Ampolon nucleophile through a donor species, and this is your acceptor Synthon, and this is in principle named as stator reaction, where you use the n heterocyclic carbene, a standard n heterocyclic carbene structure. I am now drawing it here, which is basically if you remember the mechanism of benzoin condensation, it is similar kind of mechanism, and this is one heterocyclic carbene where this particular hydrogen is the key factor for its main activity. Stator reaction mechanism we are not going to discuss in detail. We already have it we already did discuss the mechanism earlier. Now, what I am trying to do, I will analyze a similar kind of synthetic equivalents. Now, here I will give a target molecule, I am saying I am giving you a target molecule is alpha beta unsaturated aldehyde. Now, the starting material which was given to you a simple propanaldehyde. So, in terms of synthetic equivalents, if you have to do the disconnection, what basically you need? You need a this kind of vinylic anion as your donor species, vinylic anion as donor. It is a definitely difficult to visualize, but this was first reported by Professor Corey in this way. He first take this compound whose name is epichlorohydrin, react with 2 equivalent of MESNA, methanethiol, it is sodium salt. So, initially epoxide opening will takes place by MES minus as well as SN2 with this Cl. So, you will basically get MES, epoxide opening will give you the alcohol and this SME. Then free hydroxy was protected as a sodium hydride and methyl iodide. Now, this reaction was give you this methoxy protected ether. Then LDA was used as a reagent to facilitate one equivalent of methanol elimination from this OMe and H. Now, this elimination basically gave you a allyl vinyl sulfide. Now, here if you react this allyl vinyl sulfide with one equivalent of base, then you see how this reaction takes place. So, you have a allyl this and vinyl, you react with a base. Initially this hydrogen will be abstracted and will basically getting this carbon ion. Now, this carbon ion is stabilized to give you a canonical structure or symmetrical structure. So, this is very much stable carbonium ion, symmetrical carbonium ion. Now, this things was reacted with this your N propanol. So, N propanol reacts and then initially what you get? You get this OH, you get this SME and SME. Fine. Now, eventually a water molecule was reacted here and it was found that this nucleophilic water initially attacking to this vinyl sulfide to undergoing this kind of elimination, and then after this elimination you basically get this SME and OH. Now, this is what? This is basically a thioacetal. Is a thiol is there and a OH is there. So, now you simply deprotect this thiol with Hg2 plus followed by aqueous workup, you will get OH. This compound is simply is a acetal, which will instantly open it up and will give you the required compound. So, in the whole process you can basically formulate this initial compound which have been synthesized, this allyl vinyl sulfide was the equivalent of this vinylic aldehyde. So, whole process was basically it was acting as a D3 kind of synthon, D3 kind of synthon definitely, and this is a donor species, donor synthon reacting with a acceptor synthon. In principle, this particular synthon was used in many synthetic problems. Probably I will give you the next problem, which is based on something like this, where I am saying that how you can make this compound. If you visualize the target molecule, or then you do the simple retro. If you have epoxide as an electrophile, you react with this vinylic anion, it can open up and it will give you this compound. Now, this you can easily prepare as mentioned earlier. Okay. So, this is very simple, you can do it very straightforward way. We will try to conclude by using couple of interesting problems. I will just give it to you and let us see how you can analyze or how you can solve. The first one is simple, the second one I am giving you a this one, the third one the tertiary butyl and the bromide, which has been converted to corresponding TBU COMe. Now, if we analyze all the problems are basically based on synthetic equivalents. So, you can simply think of that in this case, if you have a MECO minus, you can do a Ampolong type of alkylation. In particular, this case the electrophile is here. So, all these cases these compounds are basically acceptor. So, this is your donor. In this case your donor should be something like this donor, and in this case your donor will be again the same MECO minus. Then the third case you have to look about the stereochemistry. The starting compound is tertiary butyl, the cis compound. Okay. The final product which was given is a trans. That is obvious, because as you are doing SN2 reaction of this MECO minus, it always attack from the backside attack SN2. So, you get this COMe. Now, what is the source of this MECO minus? You can easily use this 1,3-dithiene chemistry of take this acetaldehyde thiol protectate, or even you can use this as a Stork O protected cyanohydrin, this also you can use. This one is very useful. This one you can use the stock O protected cyanohydrin by using this corresponding OTMS CN, and here tertiary butyl chloride, which is sterically bulky and was used as a electrophile. The reaction basically goes well. You have probably need to do a little bit refluxing, or you need to put a thermal energy. So, all this particular transformation you can easily accomplish with the help of your synthetic equivalents. So, synthetic equivalents, there are many things to be discussed, but definitely as we do not have enough time, we will try to provide you few assignments which you can solve based on this information which you shared in the class. And in the final lecture which will be given to you next, we will try to provide you a complete story, or try to basically summarize you. So, what I will try to do? I will pick up a natural product and the strategies which we have discussed till today, starting from transformation, substrate, functional group, as well as topology and stereochemistry if it is possible. Normally stereochemistry part we try to avoid, because stereochemical strategies often need a very complex molecule, and if you have a relatively complex molecule, then explanation of the stereochemical strategies will be much more beneficial. So, eventually in the final lecture we will try to give you a gist, overall gist, by taking a medium sized molecule as a target molecule, and we will try to correlate till today what we have discussed. We will try to basically summarize up. So, have a good time, till then, goodbye.